right, good morning, everyone. How did the homework go? Any questions from the homework? Okay, can you hear me?
Yes.
Yeah, okay. Any questions from the homework?
Problem 5.
Number 5, anybody else? Okay, we look at number 5 and then we proceed. Number 5, all right. So let's see what this is about. We find the area of the region in 2 ways, using integration with respect to x, then using geometry. So first I'm going to sketch the graph that they gave us. And it consists of 2 lines. This line, y equal x, so they gave it to us. And this line, right there, this is y equal 2 minus x. And this point right here, it's a 2. And they give us everything. Actually, they gave us the intersection point 1. So this is 1.
Professor?
I'm listening.
Is that number 5 from the homework?
No, I usually do number 5 from the book, always. Because
Okay.
the one on Math Lab, each student gets something different, slightly different.
Sure.
Okay, so, but this is the idea. And it's up to you to take this and run with it. Okay?
Okay.
That's the way it works. All right, so that's the way I will always do it. You guys give me the problem, I do the one from the book, and then you guys go back to your Math Lab and say, okay, she did that, how can I do the one they gave me? Very good. So where am I? All right, so we're gonna find the area in 2 ways. Okay, the first way is basically practice what we did yesterday. And the second way we're going to do it geometrically, because these are a bunch of, it's really nothing. It's a triangle, no more, no less. All right, so first we're going to do it how we did yesterday. So how we did yesterday. So we took the interval from 0 to 1, basically. That's what we did. Okay, and we split it into pieces, into rectangle, and we find the area of each rectangle. So, and we emphasized yesterday the idea of a typical rectangle. So first I want to take a typical rectangle. So I call this xi plus 1. My typical rectangle is the following. The height is from the bottom to the top. And the width is the delta x. So this from here, the delta x. So in my mind, I'm dividing the interval from the, and I'm covering it. That's really what it is in my mind. I'm covering it with rectangle. That's really what I am doing. Cover it with rectangle. And I'm finding the area of each rectangle. That's really the logic behind it. But instead of finding the area of this plus area plus this plus area, I really focus on a typical one and find the area of this typical one. So that's what we'll be calling a typical rectangle. Typical rectangle. Okay, so my first step is I'm going to find the area of a typical rectangle. So I focus on my typical rectangle. And I do everything for it. So typical rectangle. The height of it, its width, and its area. The width is always the delta x from here to here. That's my width, a little bit. So the width is the delta x. The height is from the top curve to the bottom. That's the height. Okay, now, if this is xi right here, if this is xi from here to here, it means the height from here to here, that's the bottom curve, is xi also, because here y equal x. If this is xi, it means this point here is 2 minus xi. Okay, it means that the length here, or the height of the rectangle, which is, as you can see it, is the top value minus the lower value. So it's going to be 2 minus xi minus xi. The top always minus the bottom. Ooh, sorry. It's the top minus the bottom. So now the height is 2 minus xi minus xi. The area of a typical rectangle is the height times the width. Okay, so that's really how we proceed. Now, the area is the sum of the area of the rectangle. That's really what my Riemann sum is. So it's the sum of those areas, approximately. That's the approximation of the little areas. Okay, that's the Riemann sum that approximate the area of the region. So this is, when I'm writing the sum, it means I'm adding the area of the rectangle. That's really what I am adding. And finally, the last step is what's the actual area? The actual area is, we let n goes to infinity. So we let n, it means we let the number of subdivision becomes very large. By doing this, those rectangles are so tiny that they will cover area. So we let n tends to infinity and the integral become, the area become the following integral. 2 minus x minus x. The top curve, the bottom curve. And the interval of integration are always, you ask yourself, which interval I need to divide into pieces to cover my whole region. And in this case, we have to cover it from 0 to 1. So that's really the idea behind that. The rest is easy. There is nothing more into that. So this would become the integral from 0 to 1 of 2 minus 2x dx. And now we find the antiderivative. Antiderivative of 2 is 2x. Antiderivative of 2x is 2 times a half x squared, which is going to give me x squared between 0 and 1, which is 2 minus 1 minus at the lower, which is a 0, which is equal to 1. Okay, so that's the way we are going to do a few of those problems. So that's part A. Okay, any questions? Now, I know that Math Lab usually go after this part only, but when I am going to quiz you on Friday, I will be asking you everything for some problems. And for some problems, only the formula. So I want you to be ready for this kind of answers.
I have a question real quick.
I'm listening quickly.
When you say the top, can you go back up? When you say the heights, so the height is the first the equation that's taller than the second equation. That would be the first part of the height.
I call it the top one. We're calling it the top to make it easier.
The top part, that would be the height, the top part minus the bottom part?
Yes.
Okay.
And you see why though?
Yeah, because those are the two parts that make up the height of a typical rectangle.
Because if you think about it, if this is xi represent x0. Means from here to here, because this is the curve y equal x. So it means from here to here also, if this is x, this has to be xi also. From here to here, that's the output. This is xi, the output is 2 minus xi. So you're going from, that's the height, from the top curve to the bottom curve, means 2 minus xi minus xi. You after that. That's the height.
All right.
Okay.
Thank you.
The picture is crucial, as you will see slowly. Now, geometrically, so this is part B. Geometrically, this is nothing more than a triangle. So what is the area? Because that's what we are finding. It's half the base times the height. What's the base here? The base is from here to here, which is 2. What's the height? That's the height from here to here, which is 1. which is exactly what we're doing. I mean, we're really finding the area, okay? So I will look at 2 more problems and then I will move on. Your guys asking 39 and 49. Okay. All right, so I'll do 49 first and then when I was, no, 46, sorry. So you're asking 46 and, okay. So let me look at 46. Okay, I do 46 first because it's still the simple scenario, and then I'll do the last one. So it's the region bounded by. Actually, it's not simple. And y equal 9x. All right. So this one we are gonna set up the integral but to be able to do anything, I need to sketch. Nothing, I cannot do anything here. So we sketch. Okay. Y equal x cube. We know how y equal x cube is, like an S, going like that. Y equal 9x, that's a line. At x0, it is 0. And it's a straight line. And the slope is positive, it's a straight line. So that's really my curve. And they want me to find this area. Okay. Now, what's the issue here? If I start thinking in terms of typical rectangle, what's going to be the problem in this exercise? Let's see.
Would you need to?
We don't have an X.
Repeat. You're
We
right.
don't have an X.
I still don't understand. Repeat.
We don't have an X. The upper limit and the lower limit.
An intersection point, you mean?
Yes.
Okay, let's find them. So let us find the intersection point. Okay, intersection point. Oh, this doesn't write well. Intersection point. Okay, how to find them? We said the two curve equal 9x, and we solve for x. Okay, so we said x cube equal 9x. We solve. Now, how do we gonna solve? Remember, solving most of the time, how do you want me to solve this quickly?
Solve for X.
How? Oh, let me start picking student. So you guys wake up. Andre Williams, how do you think? How do you solve for x?
You set the problems equal to each other.
I know, and then I did that.
And then you set them, so you subtract 9x and set it equal to 0, and then you factor.
Exactly. We said this equal to 0. We factor. That's what solving is. Equal to 0 means x equal to 0. X squared equal to 9. X is plus or minus 3. So we have at 0, we knew that. This is 3, and this is minus 3. So the second coordinate, whether you substitute it here or here, they should be the same. If I put 3 here, it's 97. If I put 3 here, that's 3 to the power 3, this is 27 and 27. If you don't get the same answer, it means we're doing something wrong. And this is also, if I plug it into the first equation, I will have minus 27. In the third, minus 27. So now we have our boundary. So we took care of one issue. Second issue, and I'm taking my typical rectangle. What's the problem is going to happen? Suppose I take my typical rectangle here. What's the top curve here? And what's the bottom curve? I can't hear you. So if I take my that's what's going to happen here. My typical rectangle, I have the same formula, or the formula is changing. If I am here, what's my top curve? Natalia. Okay, I will move on. If Kiana, what's the top curve? Here. If I take this rectangle, what's my top curve? Anybody?
X cubed,
X cubed. That's my top curve here. What's my bottom curve?
9x.
9x. Do I have the same thing here? If I take,
No, it's reversed.
right, this is gonna be the top is 9x, the bottom is x cubed. So I have an issue. I don't have one sum. I don't have one Riemann integral in this case. The problem is really changing because my typical triangle is actually rectangle is really changing. So what we're going to do this, we're gonna split the problem. So we're gonna split like this. If x is between, right here, -3 and 0, the top curve is x cubed. The bottom is 9x. That's what the picture happened. Now, if x is between 0 and 3, problem is changing. The top curve is 9x. The bottom is x cubed. So to compute the area, I need actually to do this. I have to compute this area by itself, because there is one formula for it, and this area by itself. So I'm gonna call this S, and I'm gonna call this R. So we have to compute two different areas. All right, so the total area is, the area of R plus the area of S. What's the R? For R, my top curve is x cubed. My bottom is 9x. My interval is from -3 to 0. So from -3 to 0 of x cubed minus 9x dx plus from 0 to 3 of x cubed, I meant 9x minus x cubed dx. Okay, so we have to split. We don't have any choices, but we have to split in this particular scenario because here my typical rectangle, the formula is changing. I don't have one across the board. All right. Now 39, I will not do it because I think 39 is verbatim the same approach as this problem. I will have a look at it. No, 39 is the typical problem, is upper minus the lower. So I will let you guys work with it yourself. Okay, any questions before we proceed? Okay, we're gonna proceed along the same line with a switch. So in this problem, we had to find the area. We had to split into two pieces. We have no other way out. That's absolutely the way to go. Sometimes I'm gonna give you a problem on the board that I want to ask you how we do it. And then the question is, can we go around what we did? So let me take the following problem. Let me consider the region bounded by. Let's consider the region bounded by the graph of x equal y squared and y equal x minus 2. Okay, that's the region I'm going to consider. I will graph it for you here. And then I'm going to ask you to give me the area. So let's see how the graph is. X equal y squared. Be very careful here. X a function of y. X a function of y. So that's how does the graph of x equal y squared look like? Watch, if x is equal y squared, so that's the one I want to graph. Do you guys know how it looks like? So instead of being y equal x squared, x equal y squared. So if I solve, this is gonna give me y equal plus or minus the square root of x. Am I right? So it's gonna give me either y is the root x, y is minus the root x. So when I'm gonna solve this, I'm gonna have two branches. Y equal root x, that's the part, and y equal minus root x. So x equal y squared is basically the parabola, which is actually turned around. So that's y equal x. So this one here, that's the y equal root x. This one down here is y equal minus root x. So that's the graph of y equal x equal y squared, x as a function of y. Now, y equal x minus 2 is just a straight line. At 0, it's minus 2. So we're starting from here. The slope is positive. So that's the line. And this is the region I am interested in. Okay. Now, the intersection point, I will just give them to you now. I will show you later how to find them. So the intersection point are the following. 1 minus 1, I think. Yeah. So this is 1 minus 1, and this one 4, 2. Okay. Now I'm going to ask you, just no Riemann sum, just I want you to set up the integral to find the area. So the question is, set up the integrals to find the area. All right. Ideas. How do you want me to do that? Okay, what's the issue? And I don't know. What do you want me to do?
Maybe we could start by making a typical rectangle again.
Yeah, we're gonna do that. Okay, what's the problem with my typical rectangle?
The problem is that below y equals 0, it's minus the square root of x, and above it, it's positive square root of x.
Up to where? Have to be very careful. Is it, what's the top curve here in this problem? What's the top curve? So I need the whole area. Means I need to cover everything between 0 and 4. That's really, if I want to cover it with rectangle, I have to cover it, I have to divide the interval 0 to 4 into pieces so I can cover the whole my region. Now between 0 and 4, what's the top curve in this problem?
Y equals square root of x.
What's my bottom curve? What's the bottom?
X minus 2.
No, be very careful. It's x minus 2, not all the time. Watch the bottom curve. It's changing. The bottom curve is changing. It's this piece, then it's that piece. So the bottom curve is absolutely changing. So if I am gonna take a rectangle here, a typical rectangle here, that's the top and that's the bottom. If I take my typical rectangle here, that's the top and that's the bottom. So I don't have one formula that's gonna work for this and that at the same time. So what I'm gonna do, to be able to find the area, I have to split into two pieces. I have to split into two pieces because my bottom curve is changing. I have to split, and the splitting, if this is 1, it means up to 1. So now to find this, I need to find, as like I did in the previous problem, I have to find this area by itself, and I have to find this one. So I'm gonna call this R, and I'm gonna call this S. The reason is I don't have one formula that work. If I look my rectangle, the top is always the same as the bottom, which is changing. Now let me analyze that carefully. If x is between 0 and 1, what is my top curve? And what is my bottom curve? Emilia?
Would it be top would be square root of x, and then bottom would be negative square root of x?
The top is the square root. The bottom is the minus square root. Absolutely. Absolutely. That's the top in the first scenario. But that's the bottom, which is minus. That's the top, and that's the bottom here, which is x minus 2. So it's absolutely changing. I don't have a unique formula. Splitting is in order. I have to split. So between 1 and 4, between 1 and 4, my top is always square root of x because we knew it didn't change. My bottom is x minus 2. That's really my picture. So now the total area is the area of the first region that I called R plus the area of S. I have to split. Now, the area of R is, as I said here, again, I think in my mind, I'm really thinking about those rectangle, but that's going to give me the following integral. Between 0 and 1, integral from 0 to 1 of my top curve is root x minus my bottom curve is this, plus between 1 and 4, because I have to cover my whole region, is the root x minus x minus 2 dx. Okay. So finally, this is equal to the integral from 0 to 1 of root x minus root x is 2 root x dx plus that minus x plus 2. Okay. Now I will not really compute that. You guys can do it. This is easy. You should get 9/2 because square root of x, the derivative, antiderivative is easy. This is antiderivative is easy. So the antiderivative is really not hard. So I will not do it. So, but that's really the idea. If I want to compute this area, I have to split. The reason is, as you realize, is because things are changing. The bottom curve are changing. So my rectangles here and here don't have the same formula. So I need to split. Okay. Sometimes we can go around splitting. Not all the time. Sometimes we can go around splitting. And this is a typical problem where we will go around splitting by covering the region. Instead of covering it with those vertical rectangle, we're going to be covering it with horizontal rectangle. So the main idea today is how to find the area by covering it instead of horizontal, by covering it, instead of vertical, by covering it with horizontal rectangle. Okay, and we're going to be able to go around this by doing that. So part 2 is how to go around splitting. That's really my goal of today. So area, how to find area using what I will be calling horizontal rectangle, or sometimes we call it horizontal slices. Okay, so we're going to go around splitting by actually changing how we are going to fill our region with rectangle. Now, before I do that, I need really to prepare you a little bit because the formula will be simple once I do the preparation. All right, suppose I have 2 points on a line. Let me call this E, and I'm going to call this F. So I have a horizontal line, and these are the 2 points. I'm going to ask the same question I asked before. What's the distance from here to here? Or what's the length of this interval? Quickly.
F minus E.
F minus E. It means usually this is the right value minus the left value. The right value minus the left value. Okay, whenever you have 2 points horizontal. Now, even if, as we did for vertical, even if 0 is here, and my E is here, and my F is here, it doesn't really matter. The distance is the same formula. It's F minus E. Basically, this is the right value, and this is the left value. Okay, that's always be the case. The reason is from here to here, this is F. And from here to here, it's minus E because E is negative. So the distance from here to here is negative E. So this will give me F minus E. All right, now, suppose I'm going to draw the following. Suppose I have this the curve y equal x squared. Okay, so here y a function of x. That's going to now become important. Y a function of x. So this is my graph. So if you know the x coordinate, so this is the graph. So if you have any point, if you know the x coordinate, this is giving you the y coordinate. So it means simple. If this is 4, this horizontal distance from here to here is 4 square. So this is 4 square. It means this point is 416. So this is the formula give you the vertical distance. So if I take, and that's what we did last time. So when I call this x sub I here, then this point here is xi is the first coordinate. The second coordinate, we plug in xi in this formula, xi squared. So this vertical distance from here to here, this is xi squared. Okay, this is something I think you know. Now, let us say I'm going to do the following. I'm going to give you x as a function of y. So here x is y squared. The graph, I just drew it, was like this. That's the graph. So here x function of y. It means if I know y, if I take a point, if I know the y coordinate, the formula will give me the x coordinate. But let us understand the x coordinate. What is the x coordinate graphically? So if I take a point here, let me call it 4 this time. So if 4 is the y coordinate, what's the x coordinate? Quickly. What's the x coordinate of this point?
16.
2.
Is he
2.
correct? Is he correct?
16.
16. Why 16?
Y squared. Or
Because
4.
x is y squared. Do not confuse them. So in this scenario, when I give you x as a function of y, it means if I give you the y, it's going to give you the x coordinate. That's, be very careful, x a function of y. That's really the point. We're totally changing now. We're absolutely changing. Okay, so it means that this is 16. And graphically, what is 16? 16 is the horizontal distance from 4 all the way till you hit the graph. Crucial to understand this picture, absolutely crucial. So, right. This is your 16. So when I'm giving you x as a function of y, it means if you know the y coordinate, the formula is giving you the x coordinate of the point. So I'm giving you the y here. The x is 16. Let me try, so basically, exactly. So let me try another one. Suppose I take here -2. And I take this point here on the line. So I gave you the -2. What's going to be the x? Quickly. 4. Now x is absolutely 4. So what is 4? It's this horizontal distance from the y-axis till you had hit this line. So it should be, I mean, I should put -2 better. So you guys are fine, but I have to change. If I put -2 here, so this is 4. Okay. So now let me put it in general. So let me a little bit generalize in a way. If this is, I call this yi. Okay. And I go all the way till I hit the curve. So this is yi. What's this coordinate here in terms of yi?
yi squared.
That's yi squared. That's really, so the yi squared is this vertical, sorry, this horizontal distance, because that's the x coordinate. It's gonna give me this horizontal distance from the y-axis till I hit the curve. This is the yi squared. This is right here, the yi squared. Okay, so this is how we read when I give you x as a function of y, that's how we read it actually graphically. Okay, so it means that if you know the y, you plug it back into the equation x equals y squared, you're getting the x coordinate, which is the horizontal distance from the y-axis till you hit the curve. Okay, so that's really important for us. So now, suppose I have the following region. Can I move? Okay.
Yes.
Okay, now suppose I have the following region. And the region is bounded by 2 curves, but those 2 curves, instead of giving you y as a function of x, x is a function of y. So now let me write this down. So consider the region bounded by. Bounded. From the left by x equal g of y. The right by x equal f of y, and the lines y equal to c and y equal to d. So now I'm going to a region, but those regions, instead of giving you the graph as y as a function of x, x is a function of y, x is a function of y. And now find the area. The question is find the area. And using, usually I will not tell you using what, you will figure it out. But for now, because I'm setting the stage, horizontal slices or horizontal rectangle. So I will draw the area and I will analyze this verbatim. So let's see what we are talking about. What's my region? My region is this. So here x is a function of y. So that's one curve from the right. So that's the right curve. I call it xr is f of y. So in this curve, if you know the y, the f will give you the x coordinate. And let us say j, the other one, and c equal to d. This is the line y equal to c. And this is the line y equal to d. And then here I have another curve, g. So let me see, this is g. That's my g, okay? And let me write this down. This is, I call it usually L for left, and this is g of y. Okay? And this is the region I'm interested in. And the question is to find this area, okay? The general formula. Now, in this problem, what we're going to do is, so this is the x and that's the y-axis. Instead of dividing the interval on the x-axis, which will give me nothing, I'm going to divide the interval on the y-axis into pieces. So I'm going to divide this into pieces. Okay, on the y-axis. So from here to here, every piece now is not delta x anymore, it's a delta y, and that's crucial. And I'm going to cover this with rectangle, like this. like I did before, but now these are horizontal. So every rectangle starts from the left curve up to the right curve is going to be the height, and the width is going to be the delta y. These are my rectangle that I'm going to work with. Very different. And this from left to right, and this is my delta y. And I keep going. So that's how I'm going to cover my rectangle. Every rectangle starts from the left curve to the right curve. The width is the delta y. And then something like that. So I'll come. And then something like this. These are the rectangle. And now I'm going to find the area of each one of them. Add them, and get a Riemann sum. Okay? But remember here, I'm going to divide the interval between C and D, which is on the y-axis, into pieces. So every little piece here is the delta y. So these are what we're going to call the approximating rectangle. And now I need to find the area of each one. Okay, these are the approximating rectangle. To find the area of each one, I say, I'm going to take a typical one, find its area, and then add them. So right here, I'm going to start focusing on a typical rectangle, like I did before, but I'm just changing. Instead of taking them vertical, I'm taking them horizontal. So here, I'm going to analyze a typical rectangle. So I draw the curve again, and I focus on one of them. And I focus on one of them only. So the math will become easier. And this is my C. This is my D. This is the right. So yes, this is the F. And this is the G. Okay. And now I'm going to take one of those that I call my typical and find its area. So I'm going to call this YI, YI plus 1, and I'm going to find the area of this piece. Okay, that's what typical. I focus on that. All right, first let us see. From here to here, this is my delta y. Okay, so that's the width of my rectangle. Now, what's the height for or the length? The length is from here to here. How much do we have from here to here? Let us analyze it like I did. If this is yi, what's this point here? If this is yi, what's this? So I'm going to drop this down here so you can see it. How much do we have here? If this is yi, how much do we have here? I'm after this distance. I want this length. Okay, how much is this length? Okay, this little red line. If this is yi, this is the curve x equal g of y. It means this here is g of yi. Because this curve, x is g of y. So if I know the y, the formula will give me the x coordinate, which is from here to here. So this is actually g of yi. What about this point here? It's the same idea. If this is yi, x here is f of y. It means if I know the y, whatever this function is, we're going to give me the x coordinate. It's going to give me the distance from here to here. So this is f of yi. It means this length is the right curve, f of yi, minus g of yi, whatever f and g is. So if I take a typical rectangle, and the delta y is the width. So if I take the typical rectangle now, let's see what happened. Typical rectangle. The width, so now typical. And then I add the typical to get a Riemann sum. Typical rectangle. The width is the delta y. That's what the width is. The length or the height, whichever you want to call it, is the right function minus the left function. The right minus the left. So the area of a typical rectangle is the product. That's the width, and this is the height. That's a typical rectangle. Now, the area of the region, we can approximate it by what now? By the sum of the area of those rectangles. Each one of them, we know its area. So for example, the first one, I will not write this down. The first one will be f at y0 minus g of y0 times delta y. The second, f at y1 minus g of y1 times delta y. F of y2 minus g of y2 times delta y. And I'm going to add all those areas. So the area of my rectangle now is almost equal to, that's where the Riemann sum will become, almost equal to the sum of the approximating area. It means the sum of quantity like this, where my I goes from 0 to n minus 1 because I'm taking the left sum. So this is a Riemann sum. When n becomes very large, it looks definitely like a Riemann sum. So when n is becoming very large, what's going to be the area? And now we have to be very careful. So now we let n goes to infinity. We let n goes to infinity. It means when I'm saying n becomes very large, it means here I'm taking a lot of rectangle. So I'm doing a lot of subdivisions. That's the picture in my mind. Then the area will become the following integral. Now watch carefully which integral it will become. Integral of my variable, that's crucial, is y, not x anymore. Y is my variable. It's going to be f of y minus g of y. It's not x anymore. Y is my variable. Everything dy. Y is my variable. What are my limits? To find the limit, you ask yourself which interval I need to chop into pieces to cover my whole region. The interval on the y-axis between c and d. So it's going to be the integral from c to d of f of y minus g of y. And to put this in a good context, f is always the right curve, g is the left curve. And this will be the area. Okay. Now, I'm going to go back to the problem where I had to split and then do it again without splitting and show you how it works. Okay, so in this class, we will be moving back and forth. Sometimes we think of x as a function of y and sometimes y as a function of x. So we have to do both of them because we have to learn those ideas. So now I'm going to back to the initial problem I started with. And the question is, can I avoid splitting? All right. I cannot always do that. Sometimes it's impossible, but sometimes we can. So let's now go back to the original problem. The original problem. So this is my problem, the following. I will not rewrite it. That's my problem. I had this curve. This is x equal y squared. And this was y equal x minus 2. And those points were for 2. And this point here was minus 1. Okay. And when we did it previously, when I took those those vertical, I had to split because the bottom curve is changing. Now I'm going to look at it in a different eyes, and I'm going to ask you the following. I want you to think of left and right curve, not up and down. And ask yourself, is the left and right curve changing, yes or no? So let me back to you. If I think horizontally, this way, if I want to cover it with those type of rectangle, what is the left curve in this problem? Is it changing?
Y squared?
Is it changing?
No.
No. Whether I take my rectangle here or I take my rectangle here, the left curve is always the same. What about the right curve? Is it changing? Back to you.
No.
No. What is my right curve all along?
X minus 2.
Right, this line. That's my right curve. It's not changing. Regardless where I take my rectangle, that's the right curve. And that's really the left curve is not changing. It's unique. So that's the right, that's the left, and that's the right. But of course, now we have some. Now, how do we do the setup? Again, it's the same. The idea is I have to divide an interval into pieces. But the interval this time is going to be on the y-axis. Which interval on the y-axis I have to divide into pieces to cover my whole region? Who can tell me? Okay, if you don't tell me, I'll ask. Brian, have any idea? Which interval on the y-axis I need to divide into pieces so I can cover my whole region with rectangle?
From -1 to 2?
-1 all the way to 2. That's the interval. Absolutely correct. All right. Now I take my typical rectangle. I call this yi. And this the little bit, this the delta y. That's the width. And now I need to find the area of this typical one. Once I find the area of typical one, I'm honestly done. My picture is very clear. Very good. Now, this is yi. That's what I want. Okay, I want this one. It's equal to what? If this is yi, how much do I have from here to here? Do I know this point? And do I know that point? This is yi. This is the left curve. I mean, if this is yi, the x is the yi square. Now, here, if this is yi, what's this value here? Do I know it?
Xi minus 2.
No. Now I want you to be careful. No, because what's given to you? The y. To get this, what do I need? I need the x. So the first thing I need to do in those problems, if I take left horizontal slices, I need to express both curve. I should express x as in terms of y. Because in those problems, I know the y, I need the x. So step number 1 is step 1. If it's not if x is not given in terms of y, I should express it. So we need to express x as function of y. Because I want the horizontal distance. Sorry, I want, the horizontal distance. It means I need the x one. Now, x equal y squared, x is a function of y. Y equal x minus 2, x is not a function of y. I have to express it. So y is x minus 2. I need x as function. It means x equal y plus 2. That should be the first step. I need to express x as a function of y. Because now my right curve, I need the x in terms of y. It's going to be y plus 2. Now in the picture, if this is yi, then this here, from here to here, I know the y. This is the yi plus 2. That's really what the picture. So the length here is going to be yi plus 2, which is the right, minus the left. Right minus left for you to help. So now my typical rectangle, and I set up the area and we're done. So area of typical rectangle. is equal to the width, delta y. The length is the right curve, x of the right curve minus the left curve. So that's the right and that's the left. And now the total area. The total area is obtained by adding those total area. And this will give me the following Riemann sum, the following integral. Y is my variable. Be very careful, it's not x anymore. I'm splitting the interval on the y-axis. Here I will have, sorry, I wrote something that doesn't make sense. There is no 2 in here. Y plus 2 minus y squared. That's the right, that's the left. Interval. I always ask myself, which interval I have to cut into pieces to cover my region? I have to cover the interval from -1 all the way to 2. So this problem, we can do it 2 ways. Either by taking horizontal rectangle. And in this case, we integrate what we call with respect to y, and this gives me one integral. If I take those vertical rectangle, in this case, x was my variable, but then I had to split into pieces. And now I can evaluate this. That's easy integral. Give me a half y squared plus 2y minus a third y cubed. The whole thing evaluated between -1 and 2. And the rest is easy, and you should get 9/2 if I didn't do any mistake. End of the problem. Okay. And I'm very sorry I took over time. I try not to do that tomorrow. Right? Sorry about that. So your homework is on my math lab already. And good luck. I have office hours, I think, right now. So if you have any questions, you guys can go to my office hours.
Thank you.
Any questions? Thank you. All right. If you have any question, as I said, you come to my office hours. Bye-bye, guys.